Hello, this lecture is going to be on diffusion models. Diffusion models revolutionized the quality of images that generative AI could generate. In spite of that, it's just a few years old. And one thing that's very interesting about diffusion models is that they have a rich mathematics. So formal mathematical theory in many areas of deep learning is of questionable relevance to practice. It's not clear that the mathematics is describing what's actually going on. In diffusion models, it seems clear that the rich mathematics is relevant and helps with the understanding of what's going on. And furthermore, the mathematics is rich. It's kind of deep and hard, which makes a theoretician very happy, but probably does not make students very happy. So in this lecture, I'm going to go through the mathematics. It's going to be hard. It's going to involve stochastic differential equations. But I'm going to try to present the material in a way that gives intuition, even if some of the equations are a little hard to follow. I'll try hard to make the equations easier to follow, but the material is hard. All right, so a little historical comment. Diffusion models were originated in a paper in 2015, but both the theory and the results were not very exciting. The material became very prominent, very famous with this 2020 paper, Denoising Diffusion Probabilistic Models, DDPM. And I've said in a couple lectures before that faces are the easiest case of image modeling and this image generation. And this first paper did faces, sort of celebrity faces, but it made a big splash because it was done using diffusion models, which were very different from ways this had been done before. So what is a diffusion model? A diffusion model has a diffusion process, a process that makes noises noisy, makes images noisy. So you start with an image and you gradually add noise independently to each pixel of the image until the image is gone, till it's pure noise. So there's a noising process. Now the way the image is generated, remember it's a generative model that will generate an image. The modern ones generate an image in response to a prompt. Describe, give me an image of a tree in a flower garden or whatever. The way it generates an image is it starts with pure noise and maybe the prompt, but the simple case is it just starts with pure noise and turns that noise back into an image. Now, of course, if you make an image noisy and you try to turn it back into an image, you're not going to get the same image back. The theorem you want, I said the mathematics is rich, and there is a theorem. There's a theorem that says if you do this noising process very slowly with lots of layers, and you construct a model under a universality assumption that can invert each step of that process, that when you sample an image by inverting the process, you'll get a draw from the population distribution. There's going to be a theorem to that effect, that under a universality assumption for a UNet kind of model, kind of deep model, there's a theorem that says this training method under universality assumptions produces a draw from the population distribution of images. Okay, so the first thing I'm going to talk about is the diffusion process. What's this process of adding noise? So we're going to write it down in equations. So I'm going to take Z0, so Z of time is going to be an image. Z of 0 is going to be an image drawn from the population. I sample an image from the web somehow. I have some way of sampling images from the web. I sample an image. I set that image to be Z0. Here we have a cat. That's our Z0. Then I do one step of noising. Z after delta T. So Z0 is the image, Y. Y is drawn from the population. Each time I take a step, I take the image like Z0 plus epsilon, where epsilon is noise. Now this noise is, the noise itself is an image. It's noise at each pixel. So we're taking each pixel, this is an image, a value at every pixel, and that value is drawn from a normal distribution. So this is the normal distribution over the high dimensional images with the identity covariance matrix. It's saying we're adding unit variance noise to every pixel. So I take that unit variance noise and I multiply it by the square root of delta t. So if delta t is small, this is getting a very small amount of noise. For small delta t, it's just a little noise. And the stochastic differential equation happens when we take the limit of delta t to 0. So we're doing a continuum, sort of a very large number of noising steps with a very small amount of noise per step. So what happens when I add a bunch of noises together, right? So I'm taking, if I go a bunch of steps, I'm adding noise, adding a little bit of noise, then adding a little bit of noise, then adding a little bit of noise. And what happens is the variance, the expectation of the square, grows linearly in how many steps I take, in how many times I add. However, the standard deviation goes as the square root of that. So it's also true that if I add Gaussian noise and then add Gaussian noise and then add Gaussian noise, that's the same as adding Gaussian noise with the same variance, with the same sigma squared. So I can get a sample directly, skipping over a bunch of steps by adding a larger amount of noise. So adding noise and adding noise, you can always sample from the result of many additions directly by sampling from a larger noise space. You multiply your Gaussian value by a larger value. So in general, I can take an image z of t and sample from t plus n times delta t by taking z of t plus random noise, but I have to multiply that noise by the square root of the number of steps. So if each step has noise, has sigma equal to the square root of delta t, of little delta t, then this has noise proportional to the square root of n times that. So the width of the Gaussian goes as the square root of the number of things we're adding together. That's a standard fact from statistics. So when I sample directly, I take a noise whose standard deviation is the square root of the time I've waited. Okay, so if you're adding pure noise, this is the update equation. So if I tell you z of t, and then I wait for some number of steps, the size of the noise I add, the noise is going to be the sum of a bunch of little noises, but that is sort of going to average out. And the size of the step I take as a function of delta t, or n times little delta t, goes as the square root. So you can think of this random walk. There's going to be a random walk starting here when I add noise. And that random walk, the standard deviation of that random walk behaves like the square root. Now note that the square root function has an infinite derivative at 0. The square root function has an infinite derivative at 0. So if you look at a very small, if delta t is very small, these deviations are going to be much larger than delta t, sort of in the limit infinitely larger than delta t. Square root of delta t is, for tiny delta t, is infinitely larger than delta t. So this function, although it's everywhere continuous, if I plot this function, this random walk function as a function of t, it's going to be everywhere continuous, but nowhere differentiable. Because if I pick any point and pick a value at that point, the function is going to essentially diverge with an infinite variance that looks like the square root of delta t. And this is the square root of delta t. So as I let delta t go to 0, but define t to be n times delta t, I get a limit of functions. I get you get a probability distribution over functions of continuous time, right? I take this appropriate limit, delta t goes to 0, but defining t to be n times delta t, I get this continuous time limit where if I pick a point and pick a later point, it's equivalent to adding a certain amount of noise, where the size of that noise goes as the square root of delta t. So if I sample one of those functions, it's nowhere continuous. Everywhere the derivative is infinite, but I'm sorry, nowhere differentiable. Everywhere the derivative is infinite, but it's everywhere continuous, meaning for a small enough delta t, the variance is, as delta t goes to 0, this width does go to 0. It's just that the derivative doesn't go to 0. Now, if you read the literature on stochastic differential equations, it's written in a way that I find very unintuitive. So the general form in terms of delta t, so now think of delta t as being some very small delta t, is that the value of the function at t plus delta t for a general first order stochastic differential equation, or SDE, the value at t plus delta t is the value at t plus a derivative term, a linear derivative term times delta t. So this is a linear differential equation. If this is all it was, it would just be a linear differential equation. But in addition to taking this linear step, we're going to add noise. And the noise is proportional to the square root of delta t. And in general, in high dimension, this is the square root of the covariance matrix of the noise. And if you read the literature, you'll see this equation, that dz, the change in z, dz is in a normal differential equation, you'd write dz over dt. So dz equals the first derivative terms times dt, thinking of these things as differentials, plus the square root of the covariance matrix times dB, where this is a differential of Brownian motion, of isotropic unit covariance Brownian motion. These two equations say the same thing. I find this one easier to understand. But this is describing, in some sense, the limit, in the limit where you have a differential dz and a differential dt. So for a diffusion process, this is the general stochastic differential equation. The diffusion process is pure Brownian motion. We sample an image, and we get z of t plus delta t is z of t plus Gaussian noise. I'm always going to use epsilon for unit variance isotropic Gaussian noise, an independent random variable in each dimension of unit variance. And this equation now, if we take the limit of the stochastic differential equation, this equation holds for all t and all delta t. All continuous t and all continuous delta t, I can calculate the probability distribution of z of t plus delta t from z of t using this equation, where this is a random variable drawn from a unit Gaussian. So in the SDE, this holds for all t, all continuous t and delta t. And it is kind of hard to get your head around it. So in these slides, I'm going to just use this notation to mean, to talk about this stochastic process. And I'm also going to talk about, so this is just the probability of the value at t plus delta t given the value at t. And I'm also going to talk about a continuous expectation, like what's the expected or average value of f of y given z of t. So this is the expectation over drawing y from whatever its probability distribution is given z of t of f of y. And we're always going to be talking about, we're mostly going to be talking about probability distributions under the joint distribution of y and zt as defined by diffusion. Okay, now this is a lot of symbols on this slide. So what this slide is about is the mathematics of diffusion models. How do we understand this stochastic differential equation, or this process of Brownian motion starting with a sampled image? So the claim is, or the fact is, it's true, that you can formulate this as a variational autoencoder. So the last lecture was on variational autoencoders. And I'm going to go through this variational autoencoder analysis here. It's actually a hierarchical VAE. The concept of a hierarchical VAE is actually more general than diffusion models. It's quite general. It actually covers language models, as I was autoregressive language models, but we don't worry about that now. Now we're just focusing on diffusion models. But it is worth pointing out that this is a more general equation, and I love generality and I love abstraction. So this is more abstract and more general. All right, but it's not, when we start out, it's not very complicated. Here, think of y as an image and assume that we have a probability distribution over images, right? So I can define some process that samples images from the web. And the entropy of this distribution is defined to be the average or expectation when I draw from the distribution of the negative log probability of that image. I draw an image at random. I look at the negative log probability of that image, where the probability corresponds to the process of sampling. And that's the entropy of the space, the population of images, the population distribution on images. Now, I've just written this in a somewhat strange way. I've said, in addition to drawing y from the population, I'm going to draw a latent variable from an encoder distribution. Remember that a VAE has an encoder and a decoder, and it also has a prior, but here I'm going to focus on the encoder and the decoder. So I sample y, an image, I encode it into a z. This is the standard VAE analysis. I encode it into a z. I take the probability of y and I multiply and divide by the encoder probability. Now why would I multiply and divide by the same thing? What does that get me? I'll explain that in a minute. But it's clear that this equation holds because this cancels. And so this is just the expectation of drawing y of negative log probability of y, which is the entropy of y. So the entropy of y equals this expression. And here I'm treating this z as a sequence of z's, z1 to zn, where this is the diffusion process. z1 to zn is the diffusion process. So this ratio I'm going to rewrite this way, where I'm simply saying that z is a sequence defined by the diffusion process. Although this hierarchical elbow, this hierarchical VAE is again not more general than, it is more general than diffusion. So I've just written this. I can rewrite this using an autoregressive encoder, right? The diffusion process is an autoregressive encoder in the sense that it's taking y, adding noise, taking that and adding noise, taking that and adding noise. So that's stepwise. It's Markovian. To say it's autoregressive is not right. It's Markovian. Each zi determines the zi's that follow it. It's Markovian. So I've written this as I've multiplied and divided by this Markovian process. Now, there's a joint distribution. The thing about VAEs, is that there's a joint distribution on y and z. And this joint distribution can be defined, here we're defining it by the encoder, but we're going to model it by the generator, right? The generator is intended to take y and give us z such that the joint distribution on y and z is the same as you get from the encoder. So the generator is trying to model the encoder. So I can take this numerator and say, well, this numerator is defining the joint probability, is defining a joint probability defined by the population and the encoder. I'm going to turn that around and say, whatever that joint distribution is, I can rewrite it in terms of these marginal distributions. So I can start from Zn and say, well, there's some probability of Zn minus 1 given Zn under this joint distribution, and so on, all the way to the probability of y given Z1. So I've said there's some joint distribution on y and z, and I've just turned it around and written, so it's the same distribution. That's why I'm writing this as encoder, right? So this is intended to be the encoder distribution written with the chain rule in the opposite direction. So we still have equality. I've just taken the encoder distribution, written it with the chain rule in the opposite direction. Now, if I replace the encoder by a model of the encoder, I've got a cross entropy, right? I'm only doing this in the numerator, right? So I'm replacing the encoder by the generator, and the generator is going to be trained to model the encoder. And if I think of this negative log probability as, if I break it into negative log probability of the numerator minus the negative log probability of the denominator, that first term, negative log probability of the numerator, becomes a cross entropy where I sample from the encoding distribution on y and z, and I'm modeling it from the reverse distribution. Okay, so the next thing I can do, and maybe this isn't so important now, but it's worth noting that I've got a probability over Z1 in the numerator and a probability over Z1 in the denominator. And that's true for Z1 through Zn minus 1, right? Z1 occurs in both the numerator and the denominator. Zn minus 1 occurs both in the numerator and the denominator. So I can rewrite this by taking each pair, Z1 in the numerator and denominator, and writing that as a KL divergence. That's a negative log probability of a ratio of probabilities. The log probability of a ratio is a KL divergence, as long as you're sampling from the right distribution, or a negative KL divergence. In any case, we take each pair and we write it as a KL divergence. So I can write this cross entropy loss function this way. So this can become my loss function that I'm going to train the generator on. Okay, so that's a very general analysis of a general hierarchical model that applies to diffusion models. Diffusion models are now a special case. Somehow we have to train this generator process, and the generator process mathematically is going to also be a stochastic differential equation, because the theorem holds only for a complete infinitesimal stochastic differential equation. Our theorem that the reverse process actually samples from the population is going to require universality, and that we're dealing with an actual stochastic differential equation that's taking infinitesimal steps in time. But it's roughly correct. It roughly corresponds to an understanding of why these things work. So what is the distribution we want to model? We want to model the generator distribution. We want to model this distribution of P of Z1 given Z2, or generally, the conditional distribution going backward in time. So what is this backward time probability distribution? So I'm going to do two versions of the backward time probability distribution. If I go back here, this KL divergence that I got is a KL divergence between the backward probability given y and the backward probability independent of y. Okay? So what I care about, I'm going to train my generator model to minimize this KL divergence, the KL divergence from the probability given y to the probability without knowing y. So this is the probability knowing y. I'm interested in the KL divergence between these two distributions. I know this is getting long and complicated, but you can forget the math for a moment and just say, what's the training algorithm? Like if you were, show me the beef or show me what really matters. What's the code going to do, right? What's your code? So what we're going to do now is move from this very precise analytic analysis in terms of variational autoencoders to what is the code, what does the code actually do, okay? So what the code actually does is it has a training objective, and that training objective is going to be based on these two probabilities. So the training objective is going to say, well, can I calculate the probability distribution over the preceding image given this image and y? So given t, zt, and y, there's some probability distribution over zt minus delta t, the preceding one. And it's not determined because everything in this chain is noisy. So the preceding one is not determined, even given y, because the preceding one was generated by noise from y. And I'm not going to go through the derivation, but you can show that that this probability distribution is a normal distribution around zt. So if I'm going back from zt, I'm going to get a normal distribution centered at zt. Actually, sorry, it's not going to be centered at zt. It's going to be centered at y minus zt. So zt is a noisy vector. Y is the true image. If I take y minus zt, I know this is getting complicated. Y is an image. Y is the image, it's an image that I noised. I took y and I added noise. And I added noise and I got both of these numbers, both of these images, z of t minus delta t and z of t. And these are adjacent images. So I added noise to y and I got these two noisy images. Well, if I take that noisy image, I can look at the actual y and take the direction in image space from the noisy image to the original image y, right? If you think of images as vectors, there's the original vector that I made noisy and and this noisy vector. And if I go backward in time, I'm going to go directly back in the direction of the original image. That's like a linear term. But it's also going to be noisy. So I'm going to get zt plus a motion toward the original image that's proportional to delta t plus noise, backward noise. So this is still a stochastic differential equation, but now it's going back toward the image that generated it. Okay. I hope that made sense. Now, if I don't know y, then this is an average over y. So this backward probability is sort of an average over y given zt. So in that case, if I don't know y, I move in the direction of the average actual image given zt. So if zt is a blurry image of a cat, but I don't know what cat it came from, the probability distribution over the next image is sort of the average cat image, right? Because probably looking at zt, I can tell that it's a cat, or maybe even tell certain properties of the cat. If I take all the actual images that could have produced that noisy image, and if it's moderately noisy, there could be many real images that generate that noisy image. There's some average over, conditioned on the, weighted by their probability, some average over the cat images that could have generated that. And what I do is I move toward the average image given ZT. I also have to know how much noise I've added, right? ZT doesn't necessarily tell me how much noise I've added, but the correct probability this probability depends not just on ZT, but how much noise I added. Okay, so I've analyzed these two reverse time probabilities, one given Y and one not given Y. I've analyzed them and solved for them. I have an analytic solution for these reverse directions. One involves moving to the actual image, and one involves moving to the average image given ZT and T. So now what we were working with was a KL divergence. So what I'm going to do is take the KL divergence between these two distributions. Now, these two distributions have a very peculiar form, right? They're both isotropic Gaussians. They're both Gaussians around some mean. And I'm going to compute a KL divergence between these two probability distributions. These are both Gaussian distributions with the same covariance, the same amount of noise. And it turns out that that has an analytic solution. The KL divergence between these two distributions that we just solved for goes as the squared distance between the two means. Okay, I should have mentioned that this reverse process, as delta t goes to 0, we're talking about very small steps. So this is in the limit as delta t goes to 0, the limit as the steps get smaller and smaller, the limit as the step size goes to 0 and the number of steps goes to infinity, that's when these equations are exactly holding. And so we have this reverse time stochastic differential equation. So I think I said this, but I'll say it again, right? Look at this image here, the one that's not complete noise. You can probably tell that that's a cat, but you don't know that it's exactly this image. You certainly don't know that there are blinds here. So there's a probability distribution over what the original image is, given that its noisy version to noise level t is this image. And we're going to take a mean image over that distribution, this is the average image over that distribution. And okay, I said that already. Now okay. So there's a trick here. Suppose I want to estimate, suppose I want a model that's going to predict the average image given ZT. It's going to predict this is an average image given ZT. So this is still going to be a blurry image, because if I average together a lot of sharp images, I still get a blurry image. If I want to train a model to generate this, it's to generate an expectation. It turns out to be sufficient to train the model to minimize the L2 distance, the squared distance between what a value the model predicts and the target value, and a sample from this distribution. It turns out that when you minimize a squared difference, that the minimum of the squared difference is just the mean of the random variable. So if I minimize a squared distance, the model is going to generate the mean. So we can get the model to generate the mean by minimizing this squared distance. So when I said the algorithm, that I'm going to focus on what the algorithm actually does, this mathematics says that when you're doing the reverse time step, predicting the previous diffusion model from the preceding one, you don't want to train toward the actual preceding one. You can train directly to the original image, because when you train directly to the original image, the optimum of that objective function over the different possible choices of the original image results in the model moving toward the average image. So this is the objective function. We're going to train our inverter that's going to predict the previous step from T and Z by minimizing the square loss between what the step the generator takes and the original image. So assuming universality, this objective function has the property that it's going to generate the mean image. So there's a trick, if you read the literature, there's a trick the literature uses, is that instead of just adding noise, they renormalize the images to have unit pixels. Because if you just add noise, the pixels get bigger and bigger. So in practice, you can renormalize the picture to have a fixed standard size pixel. That's just, if you read the literature, you're going to run into this renormalization, square root 1 over t. But theoretically, the theory is much simpler if we ignore that. Okay, so what's our model? I said that what we're going to do is train a model to predict the actual image from ZT and from the noisy image ZT. So we're training a model to try to predict this image. Actually, we're training a model to try to predict the average of this image given this image. What is that model? It has to have some deep architecture. What architecture are we using in this model? So far, I've just said we're going to assume a universal function for making this prediction, but an actual diffusion model has some architecture. And it turns out that the architecture is what's called a UNet. And we talked about this earlier in something called Pix to Pix when we were talking about GANs, where this was originally introduced to take an image and produce a segmentation of the image. But in a diffusion model, it's used to take a noisy image and predict the original, or predict the average of the original images that noisy image might have come from. So when we go to try to predict this image from this image, what we're training is a UNet. The UNet takes this image in, and it passes it through a convnet, a convolutional neural network of decreasing spatial dimension. Now, the modern UNet might also have a transformer attention layer aspect, but for simplicity, let's assume it's a convnet. It takes this image, it passes it through a convnet to get more and more abstract representations, right? So it's getting, at the top of the convnet, it's reduced the spatial dimensions, and it's got a lower dimensional vector than the original image. And then it takes that lower dimensional representation and goes forward and tries to generate an image from it. So that's what the UNet does. It takes the image in, passes it through a convnet to get an abstract representation of the image. Then it takes that abstract representation and reconstructs an image from it. And in the reconstruction process, it has what they call skip connections, so that when I'm generating this image, I get to look at the corresponding layer of the input image, as well as the previous layer of the generation image. So this has two arrows going into it. Each one of these has the previous image and the next generation image. And this UNet is a denoising UNet. It's trying to predict, it's trained on the difference between the images it predicts and the original image that generated the noise image. So what this UNet is trying to do is minimize the squared error between its prediction based on this image and what the original image that generated this actually was. But all of this has very clean theory, right? So we go back to this KL divergence, and I got a little bit ahead of myself earlier. We go back to this expression for the entropy of H, and this KL divergence can be written as a difference between means. This KL divergence, these are both Gaussians of the same form, and the KL of the same covariance matrix, and the KL divergence is just the difference between the means of the two distributions. And what that means is the KL divergence between this, where these are the two distributions that have these two means. I just take the difference between these two means to get the KL divergence. So the KL divergence is the expectation of the norm of the difference between the means, which is just y minus the expectation of y squared. And you have to do a little bit of careful accounting to get the right dependence on delta t. So this KL divergence, if you do the right accounting, and I won't go through it, to get the right dependence on delta t, you get a KL divergence that's proportional to delta t. Okay, so now this KL divergence is proportional to delta t. So now I get a sum of this KL divergence term proportional to delta t. That's this sum here. And I can, in the limit as delta t goes to 0, we get an integral. So we get that h of y can be written this way. It's an integral of all these KL divergence terms. And we can actually just let t go to infinity. Go to positive infinity. The problem is that if you work this out, this integral from 0 to infinity diverges. So you have to pick some t0, some initial step, to get this integral to be finite. And that arises because the entropy of a continuous distribution is infinite. There's a differential entropy that is defined in such a way that it doesn't look infinite. But if you think of this as being made of real numbers, infinite precision real numbers have an infinite amount of information. So if you take this from 0, it diverges. So you can rewrite this way, where I take the standard definition of differential entropy and put it here. Or a better thing to do is say that is to simply write an expression for the mutual information between y and z of t0. And that can be written this way. So if I take this expression and subtract the entropy of y given z of t0, I get the mutual information. And that mutual information is sort of analogous to the entropy at some level of precision of the pixels. So think of this mutual information as the entropy at some level of precision of the pixels defined by the noise level of t0. A very small noise level corresponds to picking a level of precision for your numbers. So this mutual information is, you can think of it as the entropy at a specified precision of the numbers. And that can be written as an integral from whatever your precision noise level is to infinity of this expression. Okay, so this is just restating the equations I just stated. Now, there's a whole nother subject here that I'm going to save for another video and another lecture, and that's the Fokker-Planck analysis, also known as the score matching interpretation. I've presented diffusion models as variational autoencoders, and the mathematics really does correspond to this variational autoencoder analysis. This equation is derived from the variational and autoencoder analysis. But there's another framework, intellectual framework that people talk about, which is the score matching interpretation. And the mathematics behind the score matching interpretation comes from a Fokker-Planck analysis of the diffusion process. And that's a whole nother lecture, and that is also very difficult. The mathematics, the Fokker-Planck equation is pretty difficult. So I'm going to save that for a later lecture, but all I want to say here is that there is this other interpretation called the score matching interpretation, and to get the mathematics of it correctly, you have to go through the Fokker-Planck analysis of the diffusion process. And we'll save that for the next time. So until next time, well, I'll see you then.